Hello and welcome to this BioProcess International Ask the Expert webcast. I'm your host, Leah Rosen, the online editor for BioProcess International. Before we get started, just a couple of notes. This webcast is being recorded and will be made available for replay in the multimedia section of our website. We've muted the audio lines, but we welcome you to type in your questions for our speaker in the chat window on your screen. After the presentation, we will begin the question and answer portion, and I will ask our speaker your questions from the chat window. Your questions in the chat window will only be visible to myself and our speakers. So thank you for joining us today. It is now my pleasure to introduce Anthony Horlacheko and Surendra Balakai.
Good morning. Thank you, Leah. Good morning, good evening, or good afternoon, wherever you are. Thank you, everyone, for joining this conference. I'm Surendra Balakai. I'm the Senior Global Product Manager at Thermo Fisher Scientific. And today we have our speaker, Dr. Anthony Horlacheko. He's the Director of Microbial BioProcess Operations at Cytovance. Thermo Fisher and Cytovance has done a lot of collaborative work in many different areas. And definitely, this is one of the technology that's definitely interesting to look at, how it can benefit in terms of the refolding of the proteins. And Dr. Anthony is going to cover the slides. And at the end, if you have any questions regarding the mixer, I'll be happy to answer. Otherwise, on the technology part, Dr. Anthony will be helpful to answer your questions. Thank you, Anthony.
Thank you for that kind introduction, Surendra. Welcome to this webinar. I'm Anthony Horlacheko, and I work for a company called Cytovance Biologics. So Cytovance is a contract development and manufacturing organization that provides services to early-phase biotechnology clients. We help our clients through the clinical trial process towards commercialization of their drugs, and we predominantly make protein-based drugs. Our intent and motivation is to bring next-generation therapies to our clients and their patients. As of yesterday, we have 200 employees with 28 PhDs, and 100,000 square feet of lab and manufacturing facilities located in Oklahoma City in the state of Oklahoma. So what sets Cytovance apart? We are growing our company in terms of expertise, equipment, and systems. So we deliver processes and products for a wide variety of projects, some of which may be considered technically challenging. And we have 6 service areas: R&D services, our GMP mammalian manufacturing facility, our GMP microbial manufacturing facility, a flex suite that can look at transgenics or some of the more non-mainstream therapies, and a GMP clinical drug product vialing facility. Our QC area is able to do drug substance and drug product release and stability testing. I belong to the R&D services group, where we've recently announced 3 new service offerings: cell line development, process characterization, and GLP services. So today, I will talk about improving protein folding control and scalability using imPULSE mixing technology. So from this title, you should understand that we are building a device or system of devices to fold proteins efficiently. This is a scalable system to refold proteins for pharmaceutical applications. And the hope is that we can quickly develop better manufacturing processes that decrease the cost of goods, making a variety of drugs more affordable and with higher quality. In order to do this, we need to develop an understanding of the processes involved in some detail. So in this talk, I'm going to attempt to provide a simple explanation of this complex protein folding phenomenon and a rationale of how our system for protein folding is designed to work. To set the tone for today's webinar, I've added a quotation from a famous statistician by the name of George Box. The most that can be expected from any model is that it can supply a useful approximation to reality. All models are wrong. Some models are useful. So the first step in this presentation is I will define the industrial protein folding problem. Then I'll go into some detail about protein structure and how that comes to be. We can then move into what parameters must be examined and to optimize to efficiently fold a protein into an active conformation and also how we can avoid the typical pitfalls that can occur. From there, we're going to move into a discussion of the instrumentation needed to control the protein folding process. In particular, mixing, which is a challenge for scale-up. Finally, we're going to sum up where we currently are in development and our path forward. There we go. There's my pointer. So this slide is intended to provide an illustration of the structural diversity of proteins across the biopharmaceutical industry. Each is composed of one or more chains of amino acids or polypeptides that wrap around themselves in a very specific manner. The underlying structure is clearly recognizable in most of these protein representations in the form of spring-like alpha helices and ribbon-like beta sheets. The antibody structure shown here is represented as a space-filling model where each atom is represented as a sphere corresponding to the van der Waals surface, or the size of the electron cloud surrounding each atomic nucleus. All of these, you can see, have unique structures that confer the topology required for function and stability. Not only that, but the sequence of the amino acids dictates the self-assembly process resulting in that final conformation. Something I want to point out, and I'll touch on later on in the talk, is that native proteins tend to be stable in environments suitable to the mode of action, meaning that they're biocompatible. So now we're going into the, Now we're going into the industrial protein folding problem. So this is applicable to the microbial production of high-value proteins. To illustrate the extent of the problem, I'm going to talk about the Leventhal paradox. If you take a 100 amino acid polypeptide, that's about 11.5 kilodaltons, with 3 stable states around the phi and psi angles of each amino acid, that would have 3 to the power 198 different structures. Obviously, this is an extremely large number. It's more than the number of atoms estimated in the observable universe, and yet proteins can achieve this functional conformation in seconds or less. That in itself is a problem that Leventhal came up in 1958, and for 50 years it's remained an unsolved question with an incomplete understanding of how proteins do this. Much effort has been directed towards understanding this problem in the context of cells or diseases like Alzheimer's, but the industrial protein folding problem is different. Inside the cell, there are cellular quality control mechanisms such as chaperonins or disulfide isomerase, or processing of one form or another that guide the protein folding process. Also in the cell, misfolded proteins are rapidly degraded by the ubiquitin pathway. Inside an industrial protein folding system, pharmaceuticals sometimes require additives, but we can't be adding chaperonins or other proteins to this material, because anything that we do add would have to be removed to ensure the safety of the drug. So we have to, anything that is added to the protein folding process has to be studied with an analytical method and the purification process set up so that it clears that additive. Okay, so at the top of this slide is a generalized process flow diagram describing the early stages involved in pharmaceutical protein production from the microbial expression system. The product is produced in a microbial cell such as E. coli in the form of a large aggregate of inactive protein, generally termed as an inclusion body or IB. Keep in mind that the inside of a cell can be thought of as a crowded environment. The cell is triggered to produce the product polypeptides at a very fast rate, and these will largely aggregate in the cell to form an IB. So the composition of this IB may vary in purity, and the product may form complexes with other cellular components during that process. So the first step is to separate the cells from the fermentation medium, and that is harvest them by centrifugation. Before I get too far along, I just wanted to point out an important parameter. I want to mention that culture temperature has been shown to influence the ratio of the product that can form these IB aggregates compared to the amount that is produced in the cell that remains soluble. So temperature is clearly an important factor in the aggregation and soluble protein system. The next step is to break the cells. Then we isolate the IB from the cell components using various chemical systems or solutions to wash the impurities off the surface of the IB. This may occur in several steps of repeated suspension in solution and then centrifugation of the IB. So you're left with an aggregated solid of tightly bound product and potentially complex impurities. The solid is then suspended in a solution such as a chemical chaotrope or detergent, or potentially even use extreme pressure like physical forces to break the non-covalent associations that are holding that IB together. In other words, when you separate or disassociate the components of the washed inclusion bodies from each other, they're able to refold, or at least they're being prepared to refold. At the same time, there might be disulfide cross-links between these polypeptides that hold the chains of amino acids together as a covalent aggregate. So you have to add a chemical, a reducing agent, to break these disulfide cross-links between the polypeptide chains. Protein folding itself can occur using many approaches in the industrial setting. Essentially, all of these processes reduce the amount of denaturant in solution to allow the non-covalent forces in the polypeptide chains to reform, hopefully in the correct active protein structure. Aggregation is a common pitfall here that can cause other problems in addition to product loss. It can also result in challenging and expensive filtration steps that need to be put in place before purification can occur. So there is a broad variation in folding efficiency from protein to protein. And in the next several slides, I'm going to describe in some detail why this is the case. So on the right here, I have a structural model indicating 3 amino acids, the N-terminal amino group, alpha carbon, carboxyl carbon, and this R group that can be one of 20 different amino acid groups. But this is the polypeptide backbone, and these 3 amino acids are the core 1 amino acid residue. To either side, or at least inclusion of that, we have 2 planes here. These are the peptide bonds that join the amino acids together, and they form a rigid planar structure. The bonds can rotate around this phi and psi angles, and that allows the polypeptide chain to rotate and fold on itself. The primary amino acid sequence confers the protein folding topology that dictates the function of the molecule. Through these rotations of the phi and psi angles, you then get the secondary structure, and this is stabilized by hydrogen bonding. So I've shown here an alpha helix, and these dotted lines are representations of the hydrogen bonds that hold that helix together. There are other structures, such as the beta sheets and turns, that you may have seen in university biochemistry courses. And this arrow indicates that this is a right-handed helix. All of these secondary structures tend to be very compact, and they exclude water and stabilize through the intrachain hydrogen bonds. So once you have these secondary structures forming, then the tertiary structure is the orientation of these secondary structures with respect to each other in the single polypeptide chain. The quaternary structure would be if multiple polypeptide chains are folded and form a large complex. And that dictates the final topology that allows the protein to function. So moving into the forces that stabilize the protein structure, well, clearly there's the covalent bonds. I just, for example, put up the amount of energy contained in a carbon-hydrogen bond. It's 418 kilojoules per mole. It's very high. And so that chain is very, very, very strong, and it will constrain the proximity of all of these higher order interactions. The other forces that hold the protein together are the non-covalent cooperative forces. And I've put together a table here to give you a sense of what their energy is and what the effective range of distance that they are actually functional. So ionic bridges are positive negative charges, and the interaction between them, they interact at about 3 to 5 angstroms in distance, and they have a relatively high energy range of 6 to 17 kilojoules per mole. The hydrogen bonding acts at a shorter distance scale, 2.4 to 3.5 angstroms, and has an energy of 4 to 13 kilojoules per mole. The van der Waals forces are an induced dipole effect where the electron shell of one atom, if it's close enough to another atom, will be attracted to the positive charges of the other atom's nucleus. So there's a synchrony of the electron orbits that allow these attractive forces to be maximized upon contact, and the repulsive forces of the electrons and the positive charges in the atomic nuclei are less important. It has a very low energy, but since we're talking about the contact of a huge number of atoms in proteins, collectively it imparts a fairly large energy to stabilize the protein structure. The most difficult to understand is the hydrophobic interfacial effect. And let's just say that it's a long-range force that decays exponentially with distance. This is actually a kind of an outcome of the electrostatic hydrogen bonding, but it's actually very complicated. And one of the reasons it's complicated because water itself is very complicated. And the structure of water molecules in liquid water, beyond the modeling of 100 or so molecules, is currently unknown. That might come as a surprise to some of you, but I'm going to explain why in the next few slides. So let's talk about water. It's a very small molecule, 18 Daltons, and it is an oxygen and 2 hydrogens that are separated by this angle of 104.5 degrees. The electronegativity of the oxygen atom gives it a partial negative charge, so you get this dipole effect, this positive and negative charges. And the hydrogen bonds can occur in this three-dimensional tetrahedron type shape, where the electrons of the hydrogen are kind of pulled by the adjacent water molecule oxygen. And that is the hydrogen bond, and it has a distance of about 1.8 angstroms. The water molecules are very, very small, and they're polar. We saw in the previous slide that, again, that it was a small amount of energy per bond, but keep in mind that the concentration of water in dilute solutions is 55 molar, which is in gross excess of the molar concentrations of everything else. So that's a lot of energy that is contained in these hydrogen bonds in liquid water. Also, given the size of the water molecule, that means its diffusion rate is very, very fast. And the water molecules are very, very, very dynamic, and the hydrogen bonds can form and break incredibly quickly. So the average lifetime of a hydrogen bond of a water molecule at room temperature is about 5 picoseconds. So let's take a look at what we do know about liquid water structure in order to get an idea of how these proteins fold. The hydrogen bond angles I mentioned before, it's 104.5 degrees. They do not align with a perfect hexagon. As we saw in the previous slide, there was this tetrahedral form of these 5 water molecules together, and the angle between these tetrahedral axes is 120 degrees, which is the same as that of a hexagon. So in ice, you actually get the water molecules aligning in this hexagonal shape, and that is one of the reasons for the snowflake pattern and the variability. The variability comes from the fact that this angle between the hydrogens is not 120 degrees. It's imperfect, it doesn't quite align, and therefore it's a strained bond angle. And what above 0 degrees Celsius, there's enough energy in the system that these water molecules are vibrating quite a bit, and the cavity that would be generated as the ice expands below 0 degrees has this void area. It's basically just empty space. And since all of these hydrogen bonds are attractive forces, this void gets crushed in liquid water, and it's in a state of perpetual collapse. That strained bond angle is also what explains the variability in a snowflake structure, is that the propagation of these hydrogen bonds away from the central core becomes more and more energetically unfavorable, and you get these broad variations based on very, very minute distances between the water molecules that break up the hexagonal structure and allow these beautiful forms of complex structure in the snowflakes to occur. So the bottom line is that water is constrained by its structure to be a very dynamic liquid solvent. And I'd like to be able to show that in a movie. So this movie is, before I just progress, it provides a sense of the thermodynamic motion of liquid water molecules. So in this ball and stick representation, each water molecule is shown as this little V-shaped structure where the oxygen's red and the hydrogens are white. And the hydrogen bonds are shown as these green dotted lines. And the space filling model that was showed before for water was reduced to this, so you can actually see what the hydrogen bonds and how they exchange as this simulation shows. You can see right about here. There we go. There is a circular structure in the top right hand. Well, it shows that there's 6 water molecules participating in something that looks like a hexagon, but not quite. So I do want to get you to imagine this shuffling of the water molecules in 3 dimensions occurring very, very fast, showing what the dynamic nature of water is throughout the rest of this presentation. So what we're showing here, the 2-dimensional diagram here shown on the left is 2 molecules of butane. So these are carbon atoms are black, the hydrogens are white, and these are non-polar molecules that cannot hydrogen bond with water. I want you to note the ordering of the water molecules that are in close proximity to the butane. This is the hydration shell of water, and it forms a 3-dimensional cage of hydrogen bonds around hydrophobic compounds. Water molecules are highly cooperative, and the strength of their hydrogen bonds is strongly influenced by the adjacent waters. So these hydration shell water molecules have an ice-like structure, and the bonds are stronger than those in the bulk water. This was recently proved experimentally in a January 10th publication this year in the Proceedings of the National Academy of Sciences paper. And they actually measured by infrared spectroscopy and showed that these hydrogen bonds around a hydrophobic solute are very, very strong. And this first layer of water molecules is mobility constrained, essentially because it can't hydrogen bond with the butane. So this network of hydrogen bonds propagates outwards through the water molecule structure about 7 angstroms, which is the diameter of about 2 to 3 water molecules. So earlier I mentioned that the water hydrogen bonds last about 5 picoseconds. The water in the hydration shell can last about 1,000 times longer, providing a localized support for the hydrophobic moiety. So given that these hydration shell waters are mobility constrained, they can't move around. In other words, they can't move around as fast as the bulk waters. And if they try to orient themselves to hydrogen bond with the hydrophobic moiety. They can't. Given that they have kind of a ice-like structure, very stable, their normal thermodynamic mobility is transferred to the bulk water molecules. So in essence, you have what's in liquid water, a layer of ice surrounding the hydrophobic moieties and transferring that energy outwards towards the bulk water, essentially increasing the temperature of the bulk water slightly. That is energetically unfavorable. Now, I did mention that hydrogen bonds are an attractive force, so the bulk waters surrounding these hydrophobic compounds exhibit a crushing force. And what the water tries to do is it tries to constrict. And these mobility-constrained waters, any bulk water that's in between them, is outcompeted by the bulk water surrounding them. And that drives these hydrophobic moieties closer together and effectively minimizes the surface area of the waters, the number of water molecules that are ice-like and constrained. That hydrophobic force reduces the entropy of the system. It becomes more chaotic. More bulk water molecules have more mobility. And that is what the driving force is and why the hydrophobic force can act over long distances. Although it is exponentially decreasing the closer these molecules get together. I did want to point out that the increasing temperature increases the hydrophobic force by making more of a potential difference between these ice-like stable structures and the even more mobile bulk waters that will occur with increasing temperature. Air itself is hydrophobic, and that's one of the reasons why bubbles are typically spherical. They have a minimum surface area to volume ratio that is possible in nature. Okay, so now we have an idea of hydrophobic force. Let's talk a little bit more about the proteins themselves. So if you take a look at this graph here, this is a denaturation plot for IL-10, and it was taken from this paper here. So IL-10, I've just shown the structure here of one of the monomers. It actually occurs as a dimer. And if you place the pure protein in different solutions of different concentrations of a chaotrope, guanidine hydrochloride, shown here, you can get up to about 8 molar in solution. And the pure protein, the amount of unfolding of these alpha helices can be measured by circular dichroism, and that's just represented by the 0 to 100% scale, where at 0 the protein is in its native state, and the circular dichroism response will progress as the alpha helices unfold, and that alpha carbon changes how plane polarized light is rotated. Essentially, this plateau here shows that the protein is folded in its native conformation, and this plateau here is fully denatured. And you can see that you have to increase the concentration of guanidine up to about 6 molar to fully denature this molecule. And if you wanted to renature that molecule, you'd have to dilute the guanidine out to below half molar guanidine hydrochloride. And that would be a dilution factor of more than 12. This insert is very similar to the original plot, but it's a different protein. This is gamma interferon, and you can see it has a similar alpha helical structure to the IL-10, but its overall topology is quite different. And its denaturation profile is also quite different. So this curve is steeper, and it will denature over a much shorter range of concentration than the IL-10, and it has a much smaller dilution factor, and that dilution factor is quite important in terms of industrial protein purification. So now we'll move on to how you actually optimize the industrial folding parameters to make this chemical reactions occur efficiently. You have to start off with the washed inclusion bodies in order to break them apart from their aggregated state, assuming that they're already as pure as you can make them. Higher purity of the feed stream going into a folding reaction typically improves the folding efficiency. So you get a higher recovery of active product. That's just a general rule of thumb. So these pre-purified washed inclusion bodies, there's still impurities present inside them. You have to separate those chains. So you add in a guanidinium hydrochloride strong solution, about 7 molar, and that will solubilize. That will overcome those forces holding that aggregate together and will tend to linearize the polypeptides, because the water itself will exclude the guanidine molecules and force them next to the peptide bond. And that tends to linearize the fine psi angles and extend out the structure of the protein. Then you can add your reducing agent, for example, 5 millimolar dithiotritol, to eliminate these cross-links and separate these protein chains, get them ready to be refolded. The protein concentration itself, this refolding reaction is full of chemical equilibria. The product concentration, the impurity concentration, those are things that are relatively high at this point and may need to be adjusted, but that's just another way of optimizing the chemistry. The folding buffer itself, after you take these solubilized inclusion bodies and put them in solution, you're going to be then diluting out the chaotrope level and the protein level. The higher the dilution factor, the better the refolding reaction efficiency. However, large tanks are very expensive to build and to maintain. They're complicated pieces of equipment. So the practical consideration is that you can't build a swimming pool-sized tank in a manufacturing plant. It's just logistically you can't handle that much liquid easily. Other typical chemical parameters that you might optimize, I've just listed off a whole bunch here. The pH, the redox system, the any catalysts that might be present, the ionic strength. Temperature is a consideration, and the concentrations and key ratios of the components involved in the folding reaction. There might be excipients present that stabilize the structure during the fold. There might be additional chaotrope to allow the structure to breathe and reshuffle. And then there's the concentrations of the actual product, the impurities, redox components, several equilibria. But this is really covered in a lot of literature, and I think this is sufficient to say that you have to make sure the chemistry is right, and that really helps out having an efficient refold reaction. The key thing for an industrial setting is it's very difficult as you scale this process up to control mixing and the localized environments. So time becomes a very important and very, very difficult to scale. This is the key to the transition from a denatured to a folded state, and I'm going to go into that in the next slide. So let's look at the time scale of how protein folds. We've already covered the hydrophobic force and how that works, as well as hydrogen bonding. Here I have on the left side of this diagram a denatured chain of amino acids that's just represented here by these dots and backbone. The dotted lines here are the potential hydrogen bonds, and I've color-coded these so that the cysteines, the amino acids that form the disulfide cross bridges, are colored yellow. The hydrophobic components are the open circles, and the more hydrophilic R groups hanging off the amino acid side chain are colored black. So you have this straight chain, and imagine one molecule getting exposed to a water environment. Well, immediately you have the network of water molecules surrounding this and exerting a crushing force on this molecule. You can immediately see the beginnings of secondary structure forming, and that occurs in the time scale of about 0.1 to 10 microseconds. To put this in context, 0.1 microseconds, given the time scale of bulk water hydrogen bonds, 0.1 microseconds would allow a hydrogen bond to break and reform about 20,000 times. So there's a lot of activity in this water net surrounding this constricting polypeptide chain. So these initial areas of stability stabilized by the hydrogen bonds within the chain and the surrounding network of water will collapse the protein into a more and more compact structure. So the water will get excluded out the middle, and you can see here the hydrophobic residues, they get pushed together. And the hydrophilic ones that can interact with the water remain largely on the outside. And as you see this progression, pushing these cysteines closer and closer together, once they become in appropriate proximity, a disulfide bond can then form. And that is another key stabilizing feature for the protein folding. But that actual formation of the disulfide bond practically can last between seconds and hours. So in the industrial setting, what happens really quickly is that the disulfides are put into proximity. And then having the shuffling of the alpha helices and beta sheets so that the final cysteines can come together and form this disulfide chain, that's what imparts additional stability. Some proteins don't have these disulfides, and they rely solely on the non-covalent forces to form the compact structure. So I want to point out that the initial domain structures constrain later folding events by limiting the subsequent conformational options. And that it's really key here that the changing surface area of water contact during folding may actually play a key role in the progressive stabilization of the native structure. So let's talk a little bit more about mixing in a large tank. But before we do that, we're going to just look at the three initial components. Let's take a look at the water, guanidinium, and model proteins such as IL-10, and look at the diffusion coefficients. So if you take a drop of these three components, denatured IL-10 in guanidinium and water, and you look at their diffusion coefficients. The water itself has a measured diffusion coefficient of 2.3 times 10 to the negative 5 centimeters squared per second. So we can just give it a number of 1. The guanidinium is slower by a factor of 4 or so. The IL-10, that's slower by a factor of almost 1,600. So as this drop containing these three components gets put in the water, the polypeptide chains are essentially standing still while the guanidine diffuses away and the water diffuses inwards. So these polypeptide chains will remain in very close proximity and may interfere with the folding of each other and form these large aggregates so that you can get the stabilization of one chain to another rather than on itself. Clearly, diffusion alone is insufficient to separate the molten globule polypeptide chains as the soluble IBs are diluted. So we have to introduce these solubilized IBs into the refold buffer by some dispersive means. We have to mix it well. And the other thing is that we have to do this by avoiding any air that might get entrained in the process, or not by creating excessive shear forces due to the requirement of that water net being relatively stable and evenly compacting that polypeptide chain as it folds. And the way that we're trying to approach this is rapid dilution through turbulent mixing. And the idea is that we can find a way to separate those protein chains away from each other quickly and favor the inter-chain folding over the aggregation with nearby chains. So bottom line, we reduce the proximity of the folding chains and also quickly reduce the chaotrope concentration around the molten globule. Now I'd like to introduce a physics parameter. This is turbulence, and talk about it in terms of a measurement of turbulence called Reynolds number. So if you take a flow of liquid through a straight pipe, a smooth pipe of diameter L, and you change the flow rate of liquid moving through that pipe, it will affect the mixing rate within the pipe. So at low flow rates, the force, the actual pumping force, the liquid moving through that pipe, is dominated by the viscous, the self-associative forces of the liquid water, and that will generate a smooth and constant fluid motion, or laminar flow, and that gives us a calculated Reynolds number of less than 2,000. So as we increase that flow rate, we start to see chaotic eddies start to appear, and this creates turbulence, and that increases the mixing efficiency. So there's a transition range that occurs with a Reynolds number between 2,000 and 4,000, and it's still higher flow rates. You start to change how the water interacts with each other and how it interacts with the edge of the pipe, creating shear, and that causes the increasingly forceful mixing as the flow rate increases, or turbulent flow, and that has a calculated Reynolds number of greater than 4,000. So I've just placed down here what the Reynolds number calculation is. It's a simple calculation where you can take the density of the liquid, its linear velocity, diameter of the pipe, and divided by the measured dynamic viscosity of the solution. And for water, you can use water as a good approximation for that, so it's an easy number to calculate. So we can use a short burst of turbulent mixing to separate these polypeptide chains for the initial protein folding to occur. Once that state change occurs and the polypeptide is right side out, so the hydrophilic side out and the hydrophobic side inwards, then you can allow laminar flow to allow the disulfide bonds to form and the structure to reach its completed final conformation. So I'd like to show you a movie. Here we go. Before I start the movie, I just want to tell you what you're seeing. You're seeing a pipe, and there's a needle inside that pipe that's squirting out a stream of this dye, this liquid dye. So the end of the needle is right about on the left side of the screen, and you're going to see the flow. As soon as I start the movie, you're going to see the flow of liquid start to move towards the right. And I want you to see what the interaction happens. So you can see the liquid starting to flow towards the right, and now you're starting to see the beginning of turbulent eddies occurring as the flow is increased. And as the flow gets faster and faster and faster, you see more of these eddies occurring and a rapid dispersal of the dye. So now we're proceeding out of the transition range, more towards the turbulent flow range, and you can see very quickly that dye is essentially dispersed within a very short amount of time in an area of high turbulence or flow rate within a straight pipe. So this is a way to get very efficient mixing, avoid air bubbles, and not have any parts or mechanical equipment or tools. So we're simply using physical forces to perform the mixing. And what we have in our industrial setup is convergent flow mixing for protein folding. So that involves using two pumps. We use one recirculating pump that it comes from a buffer tank, a pre-made refolding buffer, and just recirculates the fluid at a constant velocity, and that'll generate a very specific amount of turbulence that is optimized for the protein's shear tolerance range. And then we have an addition pump that adds our solubilized washed inclusion bodies into that loop at a very controlled rate through just a regular Y connector. So as I've said before, we use the turbulent mixing to separate the chains during the critical initial folding steps. The conformational changes in state occur, and then we allow the protein to be exposed to a more laminar flow environment to complete its refolding process and form any disulfide cross-links that it needs. So in this simple two-pump system, the ratio of the pump flow rates gives you what the dilution factor is. So the materials are mixed before actually entering the tank through a subsurface dip tube. And there's no interference from water and air effects, and it's very controlled, and it requires a minimum of instrumentation. So what does this look like? Well, we're starting to utilize the imPULSE technology, and this instrumentation furnishes the capabilities we need to develop a robust control strategy and make sure that our physical environment and chemical environment is correct to maximize the efficiency of protein folding. So that looks like this. There we go. Here we have an example impulse mixer and 2 pumps. There's a recirculation loop coming from the bottom of the tank, this purple line, through the pump head, and the flow is controlled through this Y connector. And this is the second pump that is pumping solubilized washed inclusion bodies into our recirculation line. Here in this red area, the solutions are mixed as they return to the tank. And so the length of this line confers the mixing time that the protein is exposed to a high turbulent condition. And then as it enters the tank through this dip tube, you can actually have the laminar flow of liquid here. So the goal here was to build this system to refold processes up to a 5,000 liter refold scale. And we wanted to test this out. So we selected the impulse mixing equipment because it uses the single-use technology to reduce our cleaning validation, which is making sure that as we turn this product or turn this equipment over from product to product, that it's always perfectly clean with a pre-sterilized bag configured as such. It leads to a lot of logistical process efficiencies and manufacturing logistics I'll just touch upon in later slides. So we didn't start out right at the 5,000 liter scale. We used a 30 liter impulse mixer scale down model of this tank and the suitable pumps for that type of system, and performed a side-by-side experiment comparing the refold performance in this type of scale-down system to our 1,000 liter manufacturing scale, and it gave us positive comparable results with enough confidence to invest in the instrumentation to do this at the 5,000 liter scale. So now I'd like to show you what this impulse mixer does in terms of its unique mixing characteristics.
The imPULSE single-use mixing system's technology is based on a reciprocating motion created by a vertically moving mixing disc. The mixing disc, an integrated part of the BioProcess container, or BPC, is designed with multiple slots and silicone flaps. The flaps open as the disc moves up from the bottom of the BPC and fluid flows through the slots of the disc. On the downstroke, the flaps close and energy is directed toward the bottom of the BPC and channeled through the space between the mixing disc profile and the vessel sidewalls. The velocity of the displaced liquid provides a robust mixing.
Okay, so now that you understand the mixing action and the upstroke and downstroke and how it uses the fluid velocity along the sidewalls to mix, you can see that this unique mixing action does not generate a vortex, and the bag itself is a single-use bag that we can configure in multiple ways in partnership with Thermo Fisher to make it appropriate for any processing requirements that we need. I just want to point out that if you are making a 5,000 liter buffer, it was recently pointed out by manufacturing director that you could be actually adding literally a ton of excipient to the tank, and this impulse mixer is very, very good at being able to solubilize very quickly a powdered component. So we can generate the solution very quickly and then use it in process immediately. So I wanted to talk about the mixing characteristics in a bit more detail. This graph here shows the mixing to homogeneity of the impulse mixer. So if you imagine this side view here, this colored simulation, the BSA solution was introduced at the top, and the solution was mixed using the impulse mixer reciprocating action to mix it to homogeneity. The material was sampled here at this point in the tank at 3 different scales: 250 liter, 1,500, and 5,000 liter scale. And you can see that homogeneity upon the introduction of that solution is reached in about 40 seconds or less, which is truly a very stunning accomplishment for something of that scale. If you take a look at a comparable impeller, a magnetically driven system, it can take way more time, 15 to 20 minutes or longer, to reach that homogeneity. So with that extended amount of time, you have a lot of different microenvironments within the tank to allow the concentrated protein chains to interact with each other and aggregate and fall out of solution. So the impeller-based systems really don't work too well. They might work for bioreactors and cells that are tolerant to that type of condition, but they're not going to be that efficient when it comes down to a folding polypeptide. So in more detail, you can compare the fluid dynamic modeling of a standard impeller, which is on the right, and you can see here the color coding indicates high degrees of shear next to the turning impeller blade. And as the colors progresses from red, yellow, green, blue, you get less and less mixing efficiency. Here is a side profile where you can see the impellers driving down the liquid through its angled blades. And again, there's an area of high shear force, high mixing. And then as you get away from this blade, there's a very, very large area where there's a very poor mixing. So that is not conducive to protein folding. You get too much difference in mixing intensity throughout the entire tank. You compare that to the impulse mixer on the left, and you can see very clearly the color is much more uniform and gentle. It doesn't have quite as many of the areas of problematic high velocity indicated as this red color. It's a much more uniform flow mixing. So the folding molecules are sensitive to very high shear forces, whether they're folding or actually even in the finished pharmaceutical. Shear forces can denature proteins quite readily. And in a folding protein, you need a stable hydrogen bonding network to create the uniform compaction forces around the folding protein chain in order to achieve the correct structure. And the impellers create bulk flow through these localized, intense motions that propagate unevenly. There's too little mixing away from the impeller, too much of the blades. And especially if you have this blade turning quick enough that you can overcome the self-associative hydrogen bond force, you get what's called cavitation, where the blades are turning fast enough and have enough energy that they're literally ripping vacuum between the water molecules and breaking those hydrogen bonds and creating air bubbles. So that's cavitation. All right, so we're almost done here. If I can get to the next slide. Here we go. At Cytovance, we've invested in two of these 5,000-liter impulse mixer manufacturing systems, so we can be able to change from one to the other, and if we do need to refold this material and transfer it and filter it to another tank, we have another tank available of equal size. These tanks are jacketed, and you can see in the configuration here, there's this device up top, and this is a powder conveyance system that really can't see the back of it, but it allows the transport of powders into the top of the bag very easily. So you literally can move a ton of sugar or arginine or other type of excipient into your tank very, very quickly and easily. And it also has an in-process monitoring system that allow you to attach a probe and measure pH, conductivity, potentially oxidation reduction potential. And that will allow you to monitor your large-scale reaction with a lot of instantaneous feedback. You can get a profile of how well your reaction is occurring in your large tank. This here is our 30-liter impulse scale-down system, and with the cooperation of Thermo Fisher, we were able to configure this so that it matches in terms of functionality exactly. It has the same instrumentation between the scales, so we can use the same probes and get very comparable information, both at small scale in the lab and large scale in the manufacturing area, to show that we have appropriate control of our process. So our path forward I want to talk a little bit about the proteins themselves, and about the industry. A recurring theme is that proteins can vary widely regarding stability, especially if mutated in the absence of selection pressure. So in a live organism, if there is a mutation, and that mutation causes the proteins not to function properly or to fold improperly, that the organism will die. That constraint is not present with today's molecular biology techniques, and the pharmaceutical industry has been moving towards altered biologics to address specific clinical needs by attaching the function of one molecule to the function of a molecule maybe from a different species. They're hoping that to get some type of hybrid effect that will treat certain specific diseases. Now, since they're altering the sequence of amino acids, they are altering the final structure, and also they're altering how the protein folds and how it achieves that final structure. So that is something that is a challenge and may actually introduce more and more instabilities into some of these drugs. And that makes it more of a challenge in the protein folding area. And that's why we invested into a state-of-the-art facility and developed our personnel and our techniques and our systems to manufacture very difficult to fold proteins for our clients in the pharmaceutical industry and generate these high-quality pharmaceuticals to give life-saving therapies. Currently, we have our 30-liter impulse mixer and systems in place that we can start our feasibility studies with any particular product immediately. And we are currently building out our 5,000-liter impulse mixers as part of a 1,000-liter fermentation site. And that should be online in Q3 of this year. So I'd like to thank our parent company, HepaLink, for investing in us and their commitment. So that's fueling our growth and allowing us to get this fancy equipment to do protein folding right. And all of the employees of Cytovance for their dedication and support and collaboration. Thermo Fisher was very enthusiastic when it came to the customization of their impulse mixers for our purposes. They're very nice to work with. They have great attention to detail and really generate good-looking machines that function well. I'd also like to thank BioProcess International for hosting this webinar. And all of you that are paying attention, thank you for your participation. I'd be pleased to entertain some questions.
Great. So we do have some questions coming in. I'm not sure. Surendra, did you want to look at those questions, or would you like me to do it?
Just go ahead and read out the questions, Leah.
Okay. So what would be the general refold efficiency? What was in case of IL-10?
Well, that's a great question, and unfortunately, that's in the realm of client confidentiality. So I'm not really at liberty to discuss that particular case.
Okay. Can you tell us how well the bag's mix flaps stand up to mechanical stress of the mixing, and is there a finite amount of time over which the mixing should occur?
Well, that's a really good question. In terms of mechanical stress, what we've seen with the impulse mixers is it's a very robust single-use system. The way that it's set up, it's meant to run for a long period of time, and it doesn't have really moving parts like a bearing that could potentially generate particulates. So in terms of mechanical stresses, there's actually very little mechanical stress because the force is evenly distributed throughout the tank very effectively. I haven't really seen any problems at all with the mixing efficiency. Regarding extractables and leachables, that is the Thermo Fisher bags. I think perhaps even Surendra might be able to address that more precisely in terms of that. But the pharmaceutical grade USP class 6 plastics are used, and there's extensive characterization of those materials.
Yeah, definitely. The films have been qualified to the standards, BPSA guidelines, and right now we are further qualifying up to the BPOC guidelines for the extractables and leachables. So definitely, it meets all the necessary criteria for the biologicals usage.
And on that first question, without revealing confidential information, can you speak to the general efficiency of the Refold?
That varies a lot depending on which protein you're trying to fold. In our direct head-to-head comparison, I can speak to the fact that we've received comparable efficiencies. We were already using in our manufacturing the convergent flow stream approach. So we were already addressing some of the turbulent mixing questions early on in the refolding process. So we ended up with the very comparable results. That does bring up an interesting point. Refold efficiency is somewhat difficult to measure. The analytical methods that are used to quantify how much product you have, since you are fairly upstream in the process, there is the potential interference from other components, and you're dealing with a very dilute solution. So quantification of refold efficiency can sometimes be a challenge and requires some analytical development in order to get a handle on how to direct the process development and make the process very efficient. And
so a question on why did you jump straight from the 30 liter to the 5,000 liter instead of trying intermediate sizes? Or?
Well, that's also a good question. We are building out a 1,000-liter facility, and we are outfitting it with the best technology that we could possibly afford. And we had done enough work at the smaller scales and also using convergent flow mixing with more conventional mixing systems to test out the overall approach. So we had high confidence that we could scale up to 5,000 liters without many issues at all.
Could you discuss what would happen with or the differences you would expect with a protein that would aggregate under an impeller scenario versus the mixed bag scenario?
That is something that I've actually seen. And what can happen is that you get severe aggregation with a standard impeller, and that can actually act as a potentially settling aggregate or a flocculating aggregate that will actually float. So you end up with a broad diversity of aggregate types, and what that does is that changes the filtration efficiency, and that's something that we actually did see in our comparisons, is that the impeller mixer changed the aggregate size distribution and created a more challenging filtration problem in multiple ways than the impulse mixer.
Okay. In your view, what will be a similar system or way to try this at a small scale of like 100 mils or 1 liter?
Yes, actually, we do have that. I built a small system that actually will be able to represent that, and that is exactly how we do the development, is using our small-scale system in order to test out the refold chemistry and the initial manufacturing parameters in terms of flow rates and shear tolerance. So that is something that we can map out and explore and develop for implementation at scale.
So it seems there would be an advantage in staging the dilution and exposure to better control the stages of refolding. Are you looking into staging the dilution exposure?
Well, that can be done by mapping out different flow rates and differential flow rates between the cross flow rate generating the turbulence as well as the addition flow rate. So there you can very, very quickly, and even going to the previous question, at small scale, look at these factors very, very quickly the system, in my experience, has been fast enough that we can actually generate way more different conditions than the analytical methods can handle. So actually, we can outstrip the process condition exploration and have to be a little bit more selective of what sample can we test for analysis, because the analysis actually takes longer.
Okay. So I think we're going to wrap it up just in the interest of time. So thank you, Anthony and Surendra. And thank you to our audience for joining with us and sticking with us. The recorded version of this webcast will be made available for on-demand viewing on our website. And as a registered attendee, you will receive a follow-up email providing you with a direct link. So thank you.
Thank you.
Thank you very much for your attention.
Thank you. Bye.
So thank you all. Goodbye.